There we go. And action. All right, so like so many problems in physics, we start out with a force diagram. We're basically going to go through the exact same process as we've done for months, if not years. So this is the ladder. So what are the forces acting on the ladder?
Wait.
All right. And so there is evenly distributed, we can assume somewhat even distribution of the weight of the ladder. If you were doing civil engineering, you would get into more specifics over how is it actually distributed, and you would look at the sag in the ladder. But we are not there, so I'm just going to put that weight smack dab in the middle. So at the 5 meter mark, we have the weight of the ladder, which, and just to make life slightly simpler, we are on some strange planet where the acceleration of gravity is 10 meters per second squared. So I have 200 newtons acting down in the middle. What other forces are acting on the ladder? Friction acting where? On what? From what? Sorry, you have to be louder. From the ladder onto the, there is no ramp, it's just a ladder. If I mistakenly called it a ramp, I apologize. It's the ladder. The whole thing is just a ladder. If it were a ladder sitting on top of a ramp, then yes, I would agree with that. Go to our checklist here, F-tong. So no other, I'll spoil that one for you. No tension, spoil that one for you.
You have normal.
From what?
The person going down on the ladder?
Yes. And so we don't know if that's, what we're trying to figure out is where that's going to be. So we have this force from the person acting down. It should be equal to his weight if he is just standing there. Assuming that he is not running up the ladder, that he is moving so slowly that the normal force acting on him is equal to his weight. Officially, person here, there's normal force acting up, his weight acting down, W of P. And so this should be 500 newtons at some distance X. Now I drew this side of the midpoint for no particular reason. I could have put him on the other side since we don't know where it is. That's what we're trying to figure out. All right, so we got that normal force done.
Would there be friction acting opposite of the direction he's going up on the ladder? So,
You mean between his foot and the ramp?
yes.
Or fell into it and the ladder?
No.
We will assume that he is beautifully balanced.
Okay.
That any friction, because if he steps forward, yes, there would be some friction acting on his foot, but we'll assume that's small enough that we're not going to worry about it.
Okay.
Unless you want to make the problem even more complicated.
No.
Okay. Because Madison doesn't want it, we won't do it. Let's see, 1, 2, 3, at least 3 more forces acting on that ladder.
Is there a normal force where the bottom of the ladder is touching the ground?
Absolutely. Which way is that normal force acting on the ladder?
It'll be up on the ladder, down on the ground.
Yep. I'm only drawing the ladder piece of it, so, but there is another, you're right, indeed, it is acting down. So we have this one acting up right here. Probably ends of 1.
case, wouldn't there be one on the wall as well?
And that's, yep. Which way is it acting on the ladder?
Up.
Down, up. Remember, normal is perpendicular, it's gotta be perpendicular to the surface. The walls.
Right, yeah. Would it be down then, I guess, or to the left?
Or left, yes, left. It won't be down, it's pushing, it's keeping the ladder from going through the wall.
Okay, yeah.
And why I'm suddenly using in here is just, that's just crazy talk, so I'm gonna switch it over to what I have been using. The Y's, I apologize for those who are writing in ink. All right, one more force. So let's see, normal force, we've got the ground, the wall, the person all touching the ladder. So we got those three normal forces right there, done. We have the weight of the ladder, done.
Would it be friction between the top of the ladder and the wall?
In real life, yes. I threw this over here to indicate that I'm making the wall frictionless. The trouble is that if we put friction right here, then it becomes very difficult to, if not impossible, to know how much of this friction is actually keeping it from sliding.
Is there friction on the bottom of the ladder and the floor?
Yes, there is, and that was this right here. I only gave you the static piece of it. Because we don't want it to slide. So we're looking for when it starts to slide, that should be the exact same place or close enough to the exact same place so when it doesn't slide. And so looking for that last point where it does not slide. All right, equations of motion. F equals ma. Hopefully that relationship is not a shock to anyone. Let's establish our coordinate system here, step by step, facades. So what's the direction of acceleration of the ladder?
Left. The bottom will be going left.
When it starts to slide. However, even though the wording is when does it start to slide or slip, we're looking for technically the point where it's not, that last point where it doesn't slide. So if it's not sliding,
There is none.
right, and so that's what we're gonna concentrate on. So acceleration, not applicable. Coordinate system. Now with no acceleration, there's no gut feeling of, oh, well, this is clearly the positive direction. We got freedom here. All our forces are horizontal and vertical, so that seems like a good way of doing it. Which way's positives? Shall we succumb to the brainwashing of the math people? I got a nod back there. All right, so we'll make these to the right I hat and up J hat. So that's the coordinate axes. Do we need to decompose any of these forces?
No.
All right, because they're all in the positive I hat direction or negative I hat direction, positive J hat or negative J hat. Now the equations of motion. Well, I know what the right hand side's gonna be. Anyone?
J hat is gonna be Y1 minus 500 newtons minus 200 newtons. And it's gonna be 0.
Yep. And I hat? Go for it again.
Friction minus Y2, I think should also be 0.
Yep. Forces to the right minus the forces to the left equals 0. Forces up minus the forces down equals 0. And James, to a point you made earlier about it would slip to the left, recognize that the bottom would slip to the left, the top would slip down. Technically, in a problem like that, there are a lot of different ways of treating it. Generally, you look at what is the center of mass doing? And the center of mass actually would be going, if it slipped at some angle like that. But fortunately, we don't have to deal with that. All right, so we have two equations of motion there. Substitution, next. Do we have an independent formula for anything up here?
Friction is gonna be mu times Y.
Which y?
Y1?
Yes. Because this is the friction acting at this point right here to evict the normal force that's acting at that same point. So y1. So mu s y1 minus y2 equals 0. So I have two equations to unknowns. So we can actually solve for all of our unknowns here without any problem. It doesn't answer the actual question, so we'll have to do something else for that. So for this first one, doing the fancy math, y1 must be equal to 700 newtons. Plugging that down there, I get us, I have the number for it, I gave that to you, 0.8 times 700 minus y2 equals 0. And so y2 is equal to 560 newtons. So I know that y2 equals 560 newtons. My friction is 560 newtons, and y1 is 700 newtons. But we're left with him. We have one more equation of motion that we need to deal with. Now, F equals ma is the classic linear equation that we're dealing with, but of course, we're dealing with rotational motion. So, torque is equal to I alpha. That is the other equation of motion that is necessary to solve this problem. So, well, I know what the right-hand side's gonna be. You can either shout out the answer or a round of applause, either one, you know.
Should be 0, right?
It should be 0 because the thing's not rotating. There is no angular acceleration, it's static equilibrium in all senses of the word. Similar to the lab that you did 2 days ago. Now torque. Torque is going to be the sum of all the individual torques. This is total torque, just like this is total force. So we need to figure out what is the torque being applied by these 1, 2, 3, 4, 5 forces here. But torque, if you flash back, is equal to R cross F. We have a moment arm and we have a force. Forces I got taken care of here. But the moment arm requires a pivot point for something that's not pivoting. Thus, in the lab, I kept changing what the pivot point was. We can make the pivot point anything we want. Now, generally, in choosing a pivot point, there are logical places to do it, and there are some others. There's no wrong answer. There are just some places that will make life a little bit simpler. Anything that will eliminate a torque, or make a torque equal to 0, I should say, is probably a good spot. The more torques I can eliminate, the better. So the question is, where should we pick as our pivot point? And it'll say that there are six different spots that we can choose for our axis of rotation. And put that in quotation marks because it's not really rotating. 6 different places which will eliminate 2 torques. Let's see if we can figure out where those are.
Right in the middle?
Right here?
Yeah.
That would make this exerting no torque. So that eliminates 1. With another spot, that might eliminate 2 torques. Down here?
Yeah.
That would do it, because neither of these is like pushing on the hinge of a door. Both of these forces have, R would be 0 for both of these forces, so that's one spot, and that might be the best spot to pick, but that's one spot where the total torque, where the torque from these two is 0. So we eliminate 2 on that one. What's another spot where we would eliminate 2 torques?
Would one be the top of the ladder, like where it meets the wall?
Right there?
Yeah.
Well, we have only one force going through that, so that would also eliminate only 1 torque.
Okay. Maybe between the two, the 500 newtons and the 200 newtons.
Between the two?
Yeah.
That would actually eliminate no torques. Now, there might be, you know, ultimately, the best spot is the one which is the way your brain is working at that moment. But that actually would not eliminate any torques. We'd still get the correct answer in the end. It doesn't matter which one we pick, but I'm just trying to save us a little bit of math here. All right, so as an analogy on the door over here, I said that picking that bottom spot's like pushing on the hinge of the door. It doesn't do any torque. If I'm really pushing right directly on the hinge, I'm not gonna open or close the door. The other thing that, I'm not pushing on the hinge now, but I'm also not opening and closing the door. I'm exerting no torque on the door, or a small amount, like negligible amount. So I don't actually have to push on the door, but if I push so that the force is directed right at that pivot point, that would also exert no torque. So where would be another spot? It's not on the ladder.
It'd be on the human. It'd be on the human.
Sorry,
On the human.
on the human? If you picked it on, as, like up here or where his feet are,
Where his feet are.
that would eliminate, so that'd be this spot right here, that would eliminate just 1 torque. And again, completely legitimate to choose that way. Just trying to get you thinking a little bit differently.
Is it the top left of the, yeah, right there.
Yep, there's another spot right there, because that and that are aimed directly at it, so that would be another place that would eliminate these 2 torques. And so we have this spot, that spot, and so at this point, just follow the arrows. So these 2 meet here, those 2 meet there, these 2, and those 2. Those are the 6 spots that would eliminate 2 torques. Personally, that's the one I would go for, but I've done the others before, you get the same answer. All right, so my total torque, I got 5 forces there, so I have, I'll call it R Y1 cross Y1 plus R friction cross friction plus R 500 cross 500 plus R 200 cross 200 plus RY2 cross Y2. However you want to label them, I've got 5 forces here, so I have potentially 5 torques. Two of these will be equal to 0. And again, this R vector here, the moment arm, is a vector from my pivot point to where the forces are applied. So here's my pivot point, and so R Y1 is 0 because this force goes straight through it. That's 0 because RY1 equals 0. Plus 0 because the moment arm from the pivot point to the friction is 0. So we set up our coordinate system with I hat, j hat like this. K hat is coming out of the board. This, in essence, we did an I hat equation and j hat equation. This is my k hat equation. Cross products, as a reminder. A cross B, the magnitude of A cross B is the magnitude times the sine of the angle between them. So, this R500, basically I have a vector from my pivot point to where that 500 Newton force is being applied. What is the magnitude